let's get on. So, like I said, we are going to do some revision today. These are the topics covered. So first thing, I don't know how many of you have heard about the linear motion equations, which can be described as the SUVAT equations. I don't know if that's SUVAT or SUWAT, I don't know. That's essentially an acronym for the equations, and it's essentially equations that describe motion with constant acceleration. So acceleration is not changing, it's a constant value. And then if that is indeed constant, then those equations hold true. Right, and these are the variables that they represent. So S is displacement, distance between the initial and the final value. U is the initial velocity. V is the final velocity. A is uniform acceleration, which needs to be constant. It can't change over time. And T is the time taken for the given displacement. Well, those are the variables that make up the different equations. There's a few definitions that we need to set out on. Velocity is the change in distance over time. So if you start, you can have an initial velocity, either that is 0 or it's a value given, and then that can change over time to another value, or it can keep constant. And we can write that as the average velocity equals the distance divided by the time it took you to walk, ride, drive that distance. And then that can be rewritten as the distance equals the average velocity times the time. And if we want to say, so you can also say that if you know your actual starting velocity and you know your final velocity, add them together, divide them by 2, and you can also get your average velocity. So these two equations can be merged into one equation. So you basically take V average in the middle equation and you put it into the top one and you simplify it and you get the equation at the bottom for displacement. So that's the first equation that you need to take note of. All right, then if we go into acceleration, acceleration is the change in velocity over time. So again, same exercise, you can take your initial and your final velocity, get the difference between them, divided by the time it took you, and you can get the average acceleration. And you can rewrite that above equation to get this V equals U plus AT. So final velocity equals initial velocity plus acceleration times time. That is the second equation that you need to take note of. All right, and like I said, the other equations can be derived from these two. So now we can go and we can play around and substitute V equals U plus AT into the S equation that we discussed first and do some hocus pocus, and we get another equation for S, which is not reliant on the final velocity. You can see the S equals half U plus V times T. You need the final velocity. Now sometimes you do not know the final velocity, and then you can use this second one, which doesn't really care about the final velocity. So you just have the initial velocity, your acceleration, and the time, and you've got those, you can calculate the displacement or the distance traveled. And we can arrange some more equations, and we get this one. So then we can take the V equation final velocity, can rearrange it a bit, put it into our one other S equation, and we can rearrange and we can get our final linear motion equation. And there's a nice summary of them all. Now, if we deal with gravitational acceleration, gravitational acceleration is a constant, 9.81 meters per second, and that's usually notated as A subscript y. Now, if we take upwards motion as positive, then G will always be negative 9.81, which is essentially acceleration downwards. All right, now there is some other notation that you can use apart from using S, U, V, T, and A, which is the dot notation. So X is usually displacement, which is S. S equals X equals displacement. And if you differentiate X, which is displacement, you get velocity, which is stand there, and you put a little dot on the X, and you get velocity. So X dot equals V, X double dot equals acceleration, because you've gone and differentiated displacement twice. 2 dots mean it's been differentiated twice, so that is acceleration. So that's a different way you can write it down. Both is correct. Either you can do A, or you can X double dot, or you can do X, or you can do S. It doesn't really matter. Just be aware that some of the problems will either use the SUVAT notation, and some of them will use the dot notation. So you just need to be familiar with those two different notations. There's just an example of how it's converted to the other notation. If you see that little subscript O means initial, so start. So the X dot subscript O means initial velocity. That is just to differentiate between your final and your initial velocity. So always just normal X dot will be velocity, at a certain time. That can be either your final velocity, whichever one is given. And then if there's a subscript 0, it means it's the initial one at t equals 0. So that 0 means t equals 0, it's initial. So that's how we differentiate between initial and final velocity.
All right, let's do an example. The question states, a projectile is launched vertically with an initial velocity of 25 meters per second. Calculate the time taken for the projectile to land back on the ground, assuming no wind or air resistance. Now, the first thing we need to do is identify our variables that they've given us. And for this question, we know that the beginning velocity u is 25 meters per second. The acceleration is the gravimetrical acceleration constant of negative 9.81 meters per second squared. And the distance is 0 meters because it ends up at the place where it starts. The SUVAT equation that we're going to use is final velocity equals starting velocity times time plus a half acceleration times time squared. We can reorder this equation as we know that the final velocity is 0, and we get an equation for time equals minus 2 initial velocity divided by acceleration. And we get a final value for time as 5.1 seconds.
Next up is angular motion. So now we've considered going into the straight line, driving a car, throwing up into the air, something that goes in a straight line. Now we're going to look at angular displacement, which essentially is something turning. That's the wheel of your car, the CD, anything that turns really. So you may have, so the angle is measured in radians, not in like grades like 90 degrees or something like that. We're going to use radians. So that is something that you need to be aware of. Your calculator sometimes can be set as radians or degrees. Always make sure that that is set correctly. I know when I was at university, I sometimes forget to either set it to radians or degrees, and then my answer is completely wrong. So always remember that when you use your calculator and you're working with radians, that it's set to radians, and if you're working in degrees, that it's set to degrees. That is something that you need to remember. All right, so angular displacement. So if something is turning, in this case a circle, you can get the displacement by taking the radius and times it by the radians. So in this case, the radians is, if you take the full circle, that's 2 pi. Full theta in this case would be 2 pi. If you multiply that by the the radius of the circle, you'll get the full circumference of the circle. So that is essentially what S is telling you. S equals radius times theta. All right, so linear motion, we defined the SUVAT equations, and here we have a different set of variables. So angular displacement is theta, and then you can go and say that's the displacement, this is angular velocity, and this is angular acceleration. So again, you can use dot notation for that, or you can use these ones, which is omega naught, initial velocity, final angular velocity is omega 1, angular acceleration, which is alpha. Again, you get these two notation groups that you can use, either the theta, omega, and alpha, or dot notation, which is theta, theta dot, theta double dot. Okay, and time continues to just be t. So we can use the same 4 SUVAT equations, and we can just apply them to angular motion, and then you convert them all to these 4. So again, theta is our displacement, and omega naught is initial velocity, omega 1 is final velocity, alpha is acceleration. And in this case, the acceleration is also constant to make these equations valid. And then, like I said, the dot notation, you can use that as well.
Right, let's do an example. A potter's wheel moves from rest to an angular speed of 20 RPM in 4 seconds. Find its angular acceleration in radians per second squared. The first thing we need to do is identify the variables that's been given to us. Now for this question, they've given us the time it takes to accelerate to 20 RPM, which is 4 seconds. We know the starting angular velocity is 0 radians per second, and they've given us the final rotational velocity, which is 20 RPM, and we need to convert that to radians per second, and we get a value of 1.885 radians per second. Next, we need to determine what equation we're going to use, and we are going to use alpha equals the difference in velocity divided by t. That will give us the average angular acceleration. We substitute the values in that we know, and we get an answer for the angular acceleration as 0.471 radians per second squared.
So we've looked at both linear motion as well as angular motion, and now we're going to try and relate these two to each other. So looking at this graph or the sketch, you can see the circle is rotating at a velocity of omega, and it's got a radius r. And then at point P, the instant velocity at that point is equal to v. So there will always be an instant velocity or linear velocity for that point P, even though it's rotating at an angular velocity. So you can always take that at point P, you can always get an angular velocity as well as a sort of longitudinal or straight component to that velocity, which is v. So it will travel a distance of one circumference, which is 2 pi radians, which we've said previously. And the time taken for one revolution can be determined through omega is the angular displacement divided by the time. So that's the same for our longitudinal displacement, where you get the total distance divided by the time. That gives you the velocity. In this case, it's just for the angular. And then you can get the tangential linear velocity. That is now the component v that we saw in that sketch, which is the distance moved divided by the time taken. And that can be simplified to omega r. So that is your rotational velocity times your radius of your circle or your circumference that you're moving. And that is the tangential linear velocity. All right, so for the case of varying velocity but constant acceleration, so that is if you're rotating at a given acceleration, that means for each second your velocity is changing, you can get a tangential acceleration as well, which simplified is the one in the box. It's exactly the same as the velocity where we had omega times radius. Now it's just alpha times radius. So moving on, we can now get another acceleration called centripetal acceleration, which is inward to the origin O. So because the velocity is a vector meaning it's got a magnitude as well as a direction, positive, negative, times, so like for instance, gravitational acceleration is a vector. It's got a magnitude, which is 9.81, and then it's got a direction, which is either positive or negative. So a change in direction of the velocity will result in acceleration. And if we consider this sketch, we can see, so v subscript naught is where we start off. That we saw is omega times r. And then for each second, you can see the little dashed arrows at a constant omega rotation. And then you can see there's an inward force going to the origin, which is omega squared radius. That is our centripetal acceleration. So as is known, acceleration is the rate of change. In this case, acceleration is given by the acceleration equals the magnitude of velocity times the rate of change of direction. So centripetal acceleration is given by A subscript C, C standing for centripetal. And the equation in the box is which you can use. We've gone and simplified it a bit as being v squared over r. All right, so the direction of centripetal acceleration is always towards the origin or the center of the circular path. That will always be the case, and there's total acceleration. The tangential acceleration part and the centripetal acceleration part, that's basically when you just get a magnitude, a vector's magnitude. You square all its components and you put it under a root, square root, and you get the value. So you get a tangential component and a centripetal component, and if you want to know the total acceleration, you use that equation at the bottom.
Right, let's do an example. A car on a fairground ride accelerates around a circular track. Calculate the distance traveled around this track if the car is accelerating around the circle at a rate of 0.15 radians per second squared. And its angular velocities at points A and B are 0.3 radians per second and 0.5 radians per second respectively. The radius of the track is given as 20 meters. The first thing we need to do is to identify the variables that's been given to us. And in this question, they've given us the angular acceleration of 0.15 radians per second squared. They've given us the initial velocity at point A, which is 0.3 radians per second, and the final rotational velocity at point B, which is 0.5 radians per second. And lastly, they've given us the radius of the track as 20 meters. Now, the equation that we can use to calculate the distance traveled is the final rotational velocity, which in this case is omega b, equals omega a squared minus 2 alpha theta, where theta is the rotational distance. Now we can rearrange this equation to solve for theta, and we get a value of 0.533 radians. Now the only thing left is to convert this radians to meters, and we know the distance s is the radius of the track multiplied by theta, and we get a final value of 10.67 meters. The question asks that we calculate the maximum speed in kilometers per hour at which a train may travel around a bend of 100 meters radius if the maximum centripetal acceleration must not exceed 0.15 Gs in order to maintain passenger comfort. The first thing we need to do is to identify the values that's been given to us. In this question, they told us that the radius of the track is 100 meters. The centripetal acceleration can also not be greater than 0.15 Gs. Gs is another unit for acceleration, so we need to convert that to meters per second squared, and we multiply 0.15 with 9.81, and we get an acceleration value of 1.47 meters per second squared. Now, in order to calculate centripetal acceleration, we can use the equation AC equals the tangential velocity squared divided by the radius. Now, the unknown in this equation is the velocity, so we rearrange the equation to solve for Vt, and we get an answer of 12.13 meters per second. The last step now is to convert our answer, which is in meters per second, to kilometers per hour, which they ask for, and we get an answer of 43.67 kilometers per hour.
So last part, mathematics review. So for those of you that forgot all this stuff, trigonometry, you should be aware of the radian measure of angles. So like I said, a full rotation or a full circumference of a circle is 2 pi, and you can see half a rotation, which is 180 degrees, is pi. So you times that by 2 and you get a full circle. And then all the different 30 degrees is pi divided by 6, 45 is pi divided by 4, 90 is half pi, etc. So again, this stuff is automatically programmed into your calculator. If you use it, please remember to set your setting to radians or degrees, because if you use sin, cos, or tan, it's going to make a difference if it's set to degrees or radians. All right, so this is just the, if you look at theta, which is the angle that we are looking at, if you look from that angle, the vertical line of the triangle is the opposite side of the triangle, and the horizontal part is the adjacent. So looking at theta, the triangle side adjacent to it, that's the bottom, and the one further opposite it is the opposite angle. And they sort of go about and notate the different ways you can use trigonometry. So then they use to notate it like sin theta is opposite over the hypotenuse, which is the diagonal one there. So, and then similarly for cos is the adjacent over the hypotenuse, and tan is the opposite over adjacent. So that is some ways you can remember how to use those, sin, cos, or tan. And then they've got a nice little helpful to remember these definitions as SOH, CAH, and TOA. So that's sin is opposite, sin is opposite over hypotenuse, cos is adjacent to over hypotenuse, and tan is opposite over adjacent. So that is from the viewpoint of the angle that you're considering. So remember, if we are considering the top point of the triangle, then the adjacent, the opposite will switch around. So always remember, that is not absolute, that will always be opposite and that will always be adjacent. It switches around depending on which side of the triangle you are looking from. All right, unit conversion. Many engineering problems is non-SI. There's a lot of problems that's in feet and pound feet and square pound feet and all that stuff. Miles per hour is another one. That needs to be in meters per second. Like they say here, you can do some conversion factors to let the units cancel, like I showed on my little paper there. So for example, there's a nice little visual. 45 kilometers, you want to make it into meters. So like I said, 1,000 meters equals 1 kilometer, so you can switch that around as you want. So then the kilometers cancel out, and then it's 1,000 over 1. 45 kilometers is 45,000 meters. So that's just, again, another way you can go about it. If units are non-SI units, then 2 conversions may be necessary. In this example, we had to convert from meters to kilometers and seconds to hours, but you can also go from miles per hour, which is from meters per second there. They just show you again, there's not just one, miles to meters and hours to seconds. And conversion factors will normally be provided. So that will be in the formula sheet for you to use.
So in summary, we had a look at linear motion equations as well as angular motion equations and how we can relate these two with each other. And lastly, we revised some trigonometry problems as well as unit conversion problems. And that's it. I am available on LinkedIn and Twitter. If you've got any questions, please do not hesitate to ask them, and I will be more than happy to answer them. Thank you very much for watching, and I will see you in the next video. Bye.